Nanotilus, generator of immersive guided tours in crowded 3D environments. Publisher, IEEE. Cite This. PDF. Ruwayda Alharbi, Ondřej Strnad, Laura R. Luidolt, Manuela Waldner, David Kouřil, Ciril Bohak. All authors. 7. Cites in. Papers. 1726. Full. Text views. Open access. Sign-in with personal account required for Save To. Under a Creative Commons license. Abstract. Document sections. 1. Introduction. 2. Related work. 3. Nanotilus, technical overview. 4. Journey planning. 5. Sparsification. Show full outline. Authors. Figures. References. Citations. Keywords. Metrics. Supplemental items. Abstract. Immersive virtual reality environments are gaining popularity for studying and exploring crowded three-dimensional structures. When reaching very high structural densities, the natural depiction of the scene produces impenetrable clutter and requires visibility and occlusion management strategies for exploration and orientation. Strategies developed to address the crowdedness in desktop applications, however, inhibit the feeling of immersion. They result in non-immersive, desktop-style outside-in viewing in virtual reality. This article proposes Nanotilus, a new visibility and guidance approach for very dense environments that generates an endoscopic inside-out experience instead of outside-in viewing, preserving the immersive aspect of virtual reality. The approach consists of two novel, tightly coupled mechanisms that control scene sparsification simultaneously with camera path planning. The sparsification strategy is localized around the camera and is realized as a multi-scale, multi-shell, variety-preserving technique. When Nanotilus dives into the structures to capture internal details residing on multiple scales, it guides the camera using depth-based path planning. In addition to sparsification and path planning, we complete the tour generation with an animation controller, textual annotation, and text-to-visualization conversion. We demonstrate the generated guided tours on mesoscopic biological models, SARS-CoV-2 and HIV. We evaluate the Nanotilus experience with a baseline outside-in sparsification and navigational technique in a formal user study with 29 participants. While users can maintain a better overview using the outside-in sparsification, the study confirms our hypothesis that Nanotilus leads to stronger engagement and immersion. Published in IEEE Transactions on Visualization and Computer Graphics, Volume 29, Issue 3, March 1, 2023. Pages 1860 to 1875. Date of publication, December 9, 2021. ISSN information. PubMed ID 348825555. DOI 10.1109/tvcg.2021.3133592. Publisher, IEEE. Funding agency. CCBY, IEEE is not the copyright holder of this material. Please follow the instructions via https://creativecommons.org/licenses/by/Ford0 to obtain full text articles and stipulations in the API documentation. Section 1. Introduction. In the wake of the pandemic outbreak, the ultrastructure of biological entities, such as the severe acute respiratory syndrome coronavirus 2, SARS-CoV-2, is no longer the exclusive knowledge of a small group of structural biologists. The broader population has become familiar with the viral architecture and its elementary building blocks. Today, the public has a better understanding of what a vaccine consists of, what different types exist, and how it contributes to acquiring immunity. Overall, public knowledge of molecular assemblies and the interest in the topic are much higher than in pre-pandemic times. Simultaneously, biologists now have better ways to depict biological structures, which can be specified using CellPack 1, Chimera X 2, or Mesoscope 3, by applying a recently introduced three-dimensional 3D rapid modeling approach for these models of the mesoscale. Ultrastructure, i.e., the details of molecular assemblies, are essential for scientific publications and molecular dynamics simulations. Thus far, these scientifically relevant models are not used for dissemination to the broader public. Biologists neither have the training nor the time to create exciting scientific content directly from their models for a broad audience. Instead, illustrative and often misleading 3D models or 2D illustrations are created for public awareness. The pipeline for science dissemination to a broad audience is performed separately, generating substantial overhead and sometimes leading to unfortunate conceptual miscommunications. However, science-generated molecular models of biological entities could be used in science dissemination directly if the dissemination process were automatized so that biologists would not require in-depth science communication training. Such dissemination would require an automatized system in which the biologist would describe the model content with plain text, which would be used with the model to generate an exciting 3D animation or an interactive 3D exploration. Our vision is to establish such a technology. The essential building elements would automatically guide a camera according to the biologist's text, and the described structures would be visually presented to the viewer. With molecular models, this becomes a non-trivial problem, as the scene is very crowded with densely packed molecular structures, which are isotropically distributed in all three spatial dimensions. An advanced visibility management strategy is necessary to sparsify the environment. Ideally, such a sparsification process preserves the scene's fundamental properties, among others, the notion of crowdedness, while securing the visibility of the selected structures. Our prior work has made it possible to automatically generate a guided tour for desktop viewing. 5. However, the perception of crowdedness has been traded for clear visibility of the discussed structures. In prior work, the viewer is placed outside the scene and peers into it. In this work, we investigate a new automatic guided tour generation that preserves the notion of crowdedness and allows the audience to become deeply immersed into the space with nanoscale details. A well-suited type of science communication employs an immersive environment with a large 360 ring operator dome stereo projection or virtual reality (VR) headsets. These display technologies convey complex 3D structural arrangements much better than standard 2D displays. They are very engaging means for science dissemination, further propelling knowledge transfer. When using a previously developed desktop-centric guided tour generation, 5, in such environments, the experience can be described as watching a movie in an immersive setting. We call this type of egocentric view an outside-in view, where the users view the entire scene in front of them. The immersion did not encompass the actual space or model being communicated, which is the challenge we address in this paper. We propose Nanotilus, a guided tour generator for immersive display environments to communicate multiscale, crowded, scientifically accurate 3D models representing the structure of complex biological entities. In addition, the generator preserves the immersive, overwhelming feeling of the environment so that, in VR, the viewer is surrounded by all structures that form the model. We call this type of egocentric view an inside-out view, where the user is placed in the middle of the scene and the scene elements are located around and behind the user. The Nanotilus guided tour generation consists of several constituents, where two components represent technical novelties. Additional components complete the necessary functionality and are taken from prior research. Technically novel is the sparsification technique, which is tightly coupled with journey planning. These two parts are coupled with a text-to-itinerary conversion and labeling from prior research. Together, all these components constitute the Nanotilus guided tour generator as a novel scientific contribution on a system level. The components have been designed to match the following set of requirements. R1. Immersion. Preserve the immersion to create a feeling that one is part of the scene. R2. Realism. Preserve the realism of the model by minimizing the sparsification effect on the scene. R3. Variety. Maximize the variety of information by prioritizing the removal of redundant structures and avoid removing unique structures. R4. Multiscale. Convey the multiscale hierarchical architecture of the biological entities. R5. Smoothness. Preserve the smoothness of the visual experience by avoiding the sudden disappearance of the scene's elements. R6. Engagement. Maximize the engagement that increases the audience's eagerness to learn. Section 2. Related work. Nanotilus employs a novel path planning and visibility management technique to generate a guided tour in an immersive environment. Our work is related to several areas where we discuss the most relevant previous studies in each of those. Smart visibility. The impediment to observing internal features due to occlusion from other objects affects many 3D data visualizations. Several methods have been proposed for occlusion management. Elmvist and Cites 6 surveyed common approaches and identified 5 major design patterns. Viola and Groller 7 compiled smart visibility techniques that either adjust optical attributes through cutaway, section, or ghosted views. 8 or alter spatial layouts using exploded views or deformations. 9. Removing parts of a 3D model may lower occlusion, but it can eliminate salient features or obscure the overall characteristics of the data. A trade-off is often determined based on the importance of the depicted features. Bruckner et al. 10 detected homogeneous regions in volumetric models and reduced their opacity to reveal high-frequency objects that they assume have higher importance. Viola and Groller 11 determined visibility based on an importance function derived from the model features. Kruger et al. 12 applied a focus plus context concept as often employed in visualizations. They modulated the transparency to combine raycasted focus and context layers separately. The approach by Lee et al. 13 automatically creates cutaway illustrations for surface meshes after an initial manual shape categorization step. Several authors have formulated visibility management as an optimization problem. Sig et al. 14 proposed a Monte Carlo technique to automatically detect the best position and parameterization of a cutaway primitive. Further, Amen et al. 15 optimized light attenuation with a single scattering in direct volume rendering to selectively illuminate and uncover essential structures. Birkeland et al. 16 determined clipping regions by fitting an elastic membrane in a force field defined by the model features. Similarly, the method by Diaz et al. 17 permits the extrusion of segmented surfaces, e.g., bone structures, from the clipping plane. Molecular models often feature a high density of information similarly as in volumetric data. Researchers most often deal with occlusion by removing some of the density, i.e., they sparsify the crowded model. Ciril et al. 18 applied 2 sparsification strategies to navigate the hierarchy of a 3D molecular model. A limitation of their work is that when the user navigates deeper into the hierarchy, more of the model is removed, leading to a reduced understanding of the crowdedness. Music et al. 19 proposed a technique for authoring cutaway illustrations of mesoscopic biological models consisting of many elementary instances. Sparsification consists of clipping objects and visibility equalization. Visibility equalization comprises a series of visualization control bars overriding the clipping state of instances according to type. We consider our sparsification approach to be an automatic visibility equalizer, where the viewer does not have to control the visibility manually. Nanotilus combines both the clipping objects and visibility equalizer into a single entity and uses heuristics to guide the sparsification process. A significant drawback of cutaway views is that they inherently eliminate portions of the data from a visualization. Occlusion management methods that alter spatial characteristics, e.g., exploded views or peel-away views, circumvent this problem. Lee et al. 20 create interactive exploded views of an elaborate 3D model. The 3D model is structured in an explosion graph encoding the displacement of parts in relation to others. Birkeland et al. 21 described the automatic creation of view-dependent peel-away views for volumetric data. Sorger et al. 22 proposed a system for producing reusable animated transitions tailored to molecular datasets. Exploded views were used to examine the layering of hierarchical structures. Finally, Elmqvist, 23, distorted the space to manage occlusion, where a spherical force field repels objects close to the 3D cursor. A follow-up user study, 24, determined that the approach has high precision and is quite time-consuming. Elmqvist's approach is similar to Nanotilus in terms of employing an influence zone around a 3D position and modifying the characteristics of the objects in the zone. Our work additionally suggests several extensions. For example, to account for multi-scale scenarios, multiple levels of influence zones, and different geometries of the zones, i.e., shells, surrounding the camera are used instead of a single-level spherical influence zone. Virtual camera control. Christie and Olivier, 25, comprehensively reviewed camera control in the context of computer graphics. In addition, Mindek et al. 26 introduced a data-sensitive navigation model to enhance medical visualization interaction. In the case of large molecular scenes, the interaction techniques must consider the multi-scale characteristics. McKinley et al. 27 determined camera movement speed as a percentage of the distance to the target, resulting in fast movement far from the object, but slow and controlled movement close to it. Moreover, McRae et al. 28 described a technique for navigating multi-scale datasets employing a cube map as an image-based representation of the nearby environment. These studies address navigation in a multi-scale environment. However, they avoid collisions, which is inapplicable in molecular biology. In molecular biology, the models are densely packed, and it is crucial to apply a visibility technique that creates a space for navigation. Trellit et al. 29 suggested a navigation strategy aimed at crowded molecular biology. They employed transparency and exploded views to deliver a clear view of the target objects. Another significant component in controlling a virtual camera is its trajectory. Several studies have investigated path planning algorithms used for road maps 30, 31, 32, 33, 34, 35. The main idea is to automatically pre-compute a probabilistic collision-free road map and use a search algorithm at runtime to determine the trajectories. Su et al. 33 used this approach for producing visually pleasing camera animations from volumetric data. Path planning is also used to address different problems in VR. An example is stereoscopic adjustments for group presentations in a cave automatic virtual environment, CAVE, as an alternative to the commonly used single-person head tracking, 36. Research in robotics is highly relevant to path planning. Depth cameras have emerged as appropriate sensors for robotic navigation in complex indoor environments, 37. For example, Galvane et al. 38 described techniques to follow targets in a dynamic environment with camera-equipped quadrotor drones. In addition, Nageli et al. 39 allowed aerial cinematography movement using multiple drones in real time with multiple on-screen subjects. In our work, we propose a path planning that creates a weighted roadmap. Instead of constructing a graph based on potential locations, we use the depth buffer to estimate these. Edges connecting locations are evaluated. Then, we use Dijkstra's algorithm to determine the optimal path. Storytelling in visualization. Animated visualizations can effectively present fascinating stories about scientific data. The survey by Chow et al. 40 focuses on storytelling literature in visualization and describes its essential elements. Ma et al. 41 presented examples of effective storytelling specifically with scientific data, using such systems as Aniviz 42. Furthermore, Wolfart and Hauser, 43, utilized interactive volume visualization for guided story creation. Thoni et al., 44, described the design and requirements for interactive storytelling within 3D geographic visualizations. Additionally, Luidolt et al., 45, proposed a graphical approach to gathering and visualizing the reasoning process for generating geological sketches. Metamorphers by Sorger et al., 22, define animation through reusable storytelling templates for molecular models. Our work builds on the molecumentary method by Ciril et al., 5. This method comprises a framework for developing documentary-style content, employing scientific visualization. The approach automatically generates fly-throughs of hierarchical molecular models such that leverages previously written expert explanations to supply an accompanying verbal commentary using text-to-speech technology. A drawback of molecumentaries, which we address in our work, is the occlusion management that removes most of the scene when presenting the internal features. Storytelling in virtual reality. Immersive and interactive VR visualizations offer significant benefits to both research and education. Slater et al., 46, have evaluated VR developments since the 1980s when the concepts were first conceived. Kirais et al., 47, used VR to provide a more immersive way to explore brain data. Boches et al., 48, presented an immersive system for interactively exploring and analyzing 3D cellular nanoscale models of the brain. Kramer and Kearney, 49, described a method for creating complex traffic scenarios to examine human driving performance. Further, Ponder et al., 50, used interactive storytelling to create an immersive VR decision training system. Immersive movies can also play a critical role in learning. For example, Parong and Mayer, 51, compared instructional effectiveness between immersive VR and a desktop slideshow. Students evaluated VR lessons as more motivating and enjoyable compared to a PowerPoint slideshow. Dooley, 52, pointed out that the freedom of users to change the view in VR generates additional challenges for the authoring of VR narratives. Jung et al., 53, examined the influence of interactivity in an educational VR experience concerning immunology learning. Although interactivity is useful in improving content engagement, it does not apply to all actions. Thus, a balance should be maintained between user control and automation. Several researchers have investigated the immersive effect of VR in data visualization. In addition, VR enables the user to gaze into the data, rather than onto the data. For example, Yang et al., 54, studied room-scale immersive networks, establishing the need for a trade-off between user engagement, physical and mental demand, and efficiency. Further, Cross et al., 55, evaluated the effect of immersion by comparing immersive scatter plot visualizations. Sorger et al., 56, discussed the advantages of an outside overview and inside detailed perspectives in exploring medical data networks. Our work complements these findings. We visualize inherently spatial data and employ novel visibility management specifically for immersive storytelling. Section 3. Nanotilus, Technical Overview. The goal of our pipeline is to automatically generate engaging guided tours through nanoscale detail as a novel, attractive form of disseminative visualization for a broad audience, from the bench directly to outreach. Soon, many 3D models of biological structures at the mesoscale can be produced by scientists for research and publication purposes. With minimal additional effort, such an outcome should be repurposed for public outreach. The minimal effort requires to formulate a plaintext script that will define the guided tour content through the model. The script has to use consistent terminology with names associated to the model elements. The generated outcome can be immediately deployed in immersive dome stereo projections or guided VR tours. In this section, we clarify the terminology of the individual components involved in a guided tour generation, Figure 2. Nanotilus expects input of two types of users, authors and viewers. The author is the writer or director of the story who provides the system with a 3D model together with a script, i.e., textual story, which are then used to generate the immersive guided tour. The viewer is immersed in VR to explore structural details described in the story. The role of the viewer is similar to an audience in a cinema or theater. Figure 1. Nanotilus entering the center of the HIV model. Several protein instances are sparsified to reveal the internal part of the model. Left, a grayscale model with highlighted proteins inside the Nanotilus hull is combined with the model's final depiction. The model is dissected by a cutting plane perpendicular to the Nanotilus hull. Right, resulting view from the Nanotilus perspective. Show all. Figure 2. High-level schematic overview of Nanotilus. The author of the guided provides the system with a 3D model, the hierarchy, and a script that contains the itinerary, the names of types that the tour should visit. Journey planning receives the script, extracts the itinerary, and builds the journey. Once the journey is created, it can control the tour by interacting with the animation controller, which provides information to the camera, sparsification, and text-to-speech conversion components based on input from the viewer and the journey. Show all. A guided tour is a sequence of stereo pair images coupled with an audio narration from a text-to-speech conversion. The stereo pair is rendered based on camera settings, sparsification settings, a model, and the associated labels. An animation controller provides information to the camera and sparsification components based on input from the viewer and the journey. A journey is the path between several points of interest with associated textual narration. These points of interest are selected structural instances of the model that are highlighted and discussed in the narration of the guided tour. The input 3D model represents the molecular biological structure of mesoscale organisms, such as viruses, at the atomistic resolution. The model may consist of several thousands of instances, each formed by millions of atoms densely packed to communicate the crowded situation in real organisms. It does not explicitly contain the water molecules that sometimes represent 50% to 90% of the volume, like in the blood plasma. Including water molecules, the scene would be completely packed. Without water molecules, there are void spaces scattered inside the model. Every model is coupled with its hierarchy. See figures 11 and 12 in the supplementary material, Appendix C, which can be found on the Computer Society Digital Library at http://IEEE-computersociety.org/10. 1109/TVCG20213133 Leaf instances at the bottom of the hierarchy comprise the geometries of individual molecules. The leaf instances assemble into more complex geometries of intermediate instances, the ancestors of an instance are all the intermediate instances on the path from that instance up to the root. Each instance is of a certain molecular type that has a particular name. A script by the author contains the names of the described types. We extract the sequence of types from the script and build an itinerary. Journey planning takes the sequence of the types in the itinerary and transforms it into a path, i.e., a sequence of 3D positions corresponding to the target instances of the itinerary types. The instances are selected based on their spatial position so that the camera can easily navigate between them. The path of points with a text snippet from the script associated with each itinerary element form a journey. If only these points are visited, the resulting camera path would likely not be as engaging. For example, after visiting one target instance along the path, a natural path for the camera would be to navigate through the model's void spaces and deviate slightly from the intended direction so that the camera does not need to travel directly through all instances obstructing the way. Navigation through void spaces minimizes the number of instances to sparsify, which subsequently preserves the model realism, R2. We can observe through anecdotal evidence that passing through void spaces of the scene increases the participants' immersion in the virtual environment. If everything is cut in front of them, the coexistence with the scene will not be as strong. Therefore, we argue that navigation through void spaces increases the immersive experience, R1. In addition, we have observed that many participants were much more engaged in the virtual environment if they were immersed in it. As a metaphorical example, using the natural void spaces to cross a forest would be a more engaging adventure than using the main road. So, navigation through void spaces increases the engagement. R6. Therefore, journey planning additionally searches for the model's void spaces and considers these void spaces for traversal during the journey. The path is subdivided into line segments, ensuring that the journey takes a specific, more detailed route through the model between instances and uses the available void space. Therefore, some points along the path are associated with a target instance and text narration, and some points are included to facilitate natural corridors in the model for the camera path. At the journey planning stage, the path is just a sequence of points. The path is not yet the specific smooth trajectory the camera will be moving along. A smooth camera trajectory is generated by fitting a higher-order curve through the path's points. The absence of the water molecules assures to a large degree the existence of natural void spaces that are then used by the camera to pass through. If the scene in a particular region is too dense for a given magnification level, an artificial tunnel will be generated by sparsification. We apply sparsification to the model around the camera so that interesting and essential instances remain visible, while superfluous instances of a particular type become temporarily hidden. Sparsification is localized around the camera, which minimizes the sparsification effect on the model, preserving the model realism, R2, and scene immersion, R1. However, filtering the instances and prioritizing the removal of redundant structures increase the variety, R3, of information displayed in the scene. In the sparsified model, the camera is still enclosed by structures to preserve the immersive experience. Some local void space always exists around the viewer. Sparsification is staged through multiple concentric shell elements surrounding the camera to avoid instances abruptly disappearing in front of the viewer and to preserve the smoothness, R5, of the presented information. Sparsification increases from the outermost shell toward the center. The innermost shell hides all instances that would otherwise hit the camera. Long genetic molecules and other fiber structures are exempt from hiding. They are pushed away from the camera trajectory to reinforce the sense of immersion further. Pushing the important structures away also minimizes the number of instances to sparsify, which preserves the model's realism, R2, and scene immersion, R1. It evokes the experience of displacing objects to cross a crowded area, which increases engagement. R6. During a journey, a user may encounter instances at different scales that represent intermediate or leaf instances in the hierarchy. To convey multiple scales, R4, to the user, multi-scale sparsification is required. Section 4. Journey planning. An immersive guided tour requires a path that visits exciting places within the 3D model. Moreover, the path should run between the instances in the model so that the camera traverses the model's natural void spaces and unnecessary sparsification is reduced. The journey planning starts by identifying a set of target instances that journey should visit. This process generates a path that connects selected instances while traversing through the model's void spaces. The journey planning is completed in a pre-processing stage, and the outcome is used during runtime with scene traversal. The detailed explanation of each step of journey planning can be found in the following subsection. For point 1, target instances determination. The first step in journey planning is to determine representative instances from the itinerary. The itinerary is extracted from the input script. The script comprises individual sentences, and type names are extracted from these sentences. Every type in the itinerary has an associated textual snippet text, T, in the narration using text-to-speech synthesis. This process is described with further detail in our previous work, where it is called the Text-to-This method, 5. The guided tour itinerary is a sequence of types T1, Tn used to determine the sequence of target instances whose 3D positions define the initial path. The initial position P0 of the camera is outside of the model, so the whole model is inside the camera frustum. For each type T, we select one particular instance C among the many by taking the one closest to the camera position pi-1. From the camera position pi, which is set to view the instance C, the closest instance C plus 1 of type T plus 1 is found. Then, camera position pi plus 1 is determined, and so on, until we find a corresponding instance C for every type T of the itinerary. This leads to sequences of target instances S equals S1, Sn, and camera positions P equals P0, Pn that form the initial path. The initial path is further refined by analyzing the possible ways through the crowded model, leading to a path with two-level indexing, where all points between pi and pi plus 1 are indexed with pi, 0, pi, m. Level 1 point pi corresponds to level 2 point pi, 0, and pi, m is the last level 2 point that connects to pi plus 1. For point 2 tunnel detection. Although the 3D model is densely packed, the camera can typically traverse through several existing holes. We employ a vision-based approach to determine the path through the holes in the model from target instance C to target instance C plus 1. We render the scene to obtain a depth image from the camera position pi, with the lookat vector pointing to the target instance C plus 1. Then we analyze the depth buffer and identify tunnels that end farthest from the camera, and their opening is sufficiently large on the rendered image. Next, we move the camera towards the tunnel, adjust the camera lookat vector to the target instance C plus 1 again, and repeat the entire process until the target instance C plus 1 has become sufficiently visible. The approach analyzes the depth and ID buffers. Both are attachments of a frame buffer object. Therefore, every time the scene is rendered, both buffers are updated immediately within a single draw call. For each pixel, the depth buffer contains the distance to the instance closest to the camera. The ID buffer contains the identifier of the rendered instance or a default value. While the background is not considered, the tunnels are detected using GPU-based connected component labeling called label equivalence 5758. The algorithm detects the regions where the voids are projected in the depth map. We refer to these regions as void depth projection, VDP. The existence of VDPs is assured as these are 2D regions detected in the depth map, which is updated in every frame based on the camera position and rotation. As the tunnels or VDPs lead to instances, their existence is assured if at least one instance is visible in the scene. In this case, the tunnel leads to that instance. Therefore, as the viewer is enclosed in the model, tunnels, as we define them, are presented during the guided tour. The label equivalence algorithm identifies which pixels in the depth buffer belong to the same connected cluster or VDP. The algorithm relies on 3 GPU functions: initialization, scan, and analysis. The initialization function uses the pixel's linear address as a unique label for that pixel. The scan function compares each pixel's depth value with its 8 neighbors to determine whether it is connected to one of them, i.e., has a similar depth value. If so, it updates the pixel label with the smallest label. Finally, the analysis function checks the label of each pixel to determine whether it refers in turn to an even smaller label. This process continues until the root of a chain of labels is found. The root label becomes the label of that pixel. The scan and analysis functions are repeated until label stability is achieved, i.e., labels are no longer updated in a pass. We also collected size and 3D position information about the detected VDPs. The analysis of the depth buffer typically provides several good tunnel candidates. For point 3 journey generator. Journey planning computes and evaluates several candidate paths for the camera to move from one 3D position to the next. Once we reach the target instance, one of the candidate paths is selected and used by the animation controller. Candidate paths are stored in a directed acyclic graph, DG, to allow efficient searching through them. Every path is given as a polyline connecting 3D points. An edge in the DAG represents a segment of the polyline. Both endpoints of a segment have corresponding nodes in the graph. Edges are weighted, which allows us to search for an optimal path. For example, edges are assigned a higher weight if they correspond to broader and longer tunnels. Journey planning processes instances C sequentially in steps. In every step, a DAG containing alternative paths between the camera position pi-1 and a 3D point close to instance C is created. Intermediate nodes and edges are inserted into G while analyzing the depth buffers in recursive calls. An example of graph G is depicted in Figure 3. A detailed exemplary description for the first instance S1 of the sequence follows. The remaining instances from S are computed analogously. Figure 3. Top left, depth buffer of the current frame. Brighter colors indicate instances farther from the camera. Bottom left, the two farthest void depth projections, VDP0 and VDP1, are used for detecting I0 and I1 and computing N0 and N1. Right, illustration of depth-based journey planning building the graph G. Intermediate points nu-Z represent nodes in the graph that are computed. Show all. In the beginning, G is created and initialized with a single root node representing the 3D camera position P0. The scene is rendered from the camera position P0 pointing to the instance S0. By rendering the scene, a frame is obtained. Then, the depth buffer of the frame is analyzed and VDPs are found as described in section 4.2. In the next step, we evaluate each VDPJ. The weight, VDPJ, is calculated as the sum of depths of all pixels belonging to VDPJ. This calculation assigns high weight to VDPs corresponding to larger and longer tunnels. For each VDP, a set of instances I equals I1, IJ, IO from the ID buffer is detected based on the pixel coordinates of the center of the void depth projection. Point nu-Z is calculated as the intersection of the line from camera P0 to instance IJ and the bounding sphere of IJ. The distance of the point nu-Z from the camera P0 can be optionally limited by a max edge length to prevent moving too far through the model. A new node, nu-Z, is inserted into graph G, referencing the intersection point. nu-Z. A new edge EJ connecting node, P0, with node, nu-Z, is also inserted. The weight of the edge EJ is set to weight, VDPJ. In the following step, the camera is placed at positions of points nu-Z, oriented toward S1. If instance IJ is a leaf instance and not an intermediate instance, IJ is hidden because it will likely block the camera view in the next iteration of the algorithm. The scene is rendered again, and the process is repeated until the target instance S1, or at least one of its leaf instances meaning S1 is visible partially, is detected in the ID buffer. In the final path refinement step, a set of leaf nodes L from G end up very near S1, and their average position lav is computed. The point P1 is set to the position of the closest point on the bounding sphere of S1 to lav, and edges previously ending in L are retargeted to P1. In addition, a reference to S1 for P1 is stored. Once G with multiple path segments is computed, the highest weighted path segment connecting P0 with P1 from G is determined. Points P0 and P1 are taken to define the level 2 points P0, 0, P0, M of the refined path. As the edges in the graph have numerical weights, we use Dijkstra's algorithm to obtain an optimal path. Finally, the temporary DAG-G structure is cleared for the next path processing step. The remaining instances C, with I as an element of 2, N, are processed analogously. The pseudocode of algorithm 1 can be found in the supplementary material, Appendix A, available in the online supplemental material. Section 5. Sparsification. When the viewer enters an immersive world of a packed mesoscale molecular biology, the scene density evokes an experience like cutting through a jungle, even if there are tunnels to pass through. Therefore, we designed a local, camera-centric sparsification procedure, reminiscent of the Nautilus submarine from science fiction because of the involved geometries and the user experience. The sparsification is controlled by 3 nested and concentric shells surrounding the camera. These 3 shells approximate the change in visibility function that varies from 0 to 1, where 0 means nothing is visible and 1 means everything is visible. We use 3 shells for illustration, but this can be generalized to an arbitrary number. Based on the overlap of the model instances with the shells, the visibility of all but a few selected instances is modulated, or the instances are entirely hidden. Nanotilus generates endoscopic views where the scene elements surround the viewer. The shells are designed as an ellipsoidal shape that is anisotropic along the tangent of the journey path. As a result, the sparsification of the model is stronger in the forward direction and weaker orthogonal to the tangent, which provides the viewer with necessary space to observe the environment. In addition, the sparsification reduces structural occlusion and provides the user with endoscopic views that convey the crowdedness in the model while offering an unobstructed journey through the model. Nanotilus performs a multi-scale sparsification to cope with the multi-scale hierarchy of the 3D mesoscale model. It detects the appropriate scale of the target instance and sparsifies the model accordingly. For example, if the target instance in the HIV model is a particular virion as an intermediate instance, the granularity of sparsification should affect other instances on the same scale, i.e., other virions. Sparsification, in this case, should not just hide some leaf instances belonging to neighboring virions. Instead, entire intermediate instances should be hidden. If a HIV capsid protein is a target instance, a natural behavior would be to sparsify neighboring virions on the intermediate instance scale. However, in the case of a target instance's parent, lower-level instances should be sparsified to open the virus and reveal the capsid protein. Thus, the sparsification granularity is modulated based on the hierarchical vicinity of an instance to the target instance. The sparsification process is performed during the guided tour execution. The camera motion frequently invokes the sparsification, which is scale-aware, i.e., based on the target instance characteristics. In the Nanotilus framework, this information is passed on to the sparsification component by the animation controller. When a new target instance is selected, the sparsification component defines the scale on which the occluding instances should be sparsified. This has been illustrated in the above examples with HIV as the target instance on the intermediate scale and the capsid protein as the target instance on the leaf scale. Spatially large target instances require stronger sparsification than spatially small instances. Therefore, Nanotilus changes the sparsification region based on the target instance. It gradually increases or decreases the dimensions of the shell geometries to match the bounding sphere size of the target instance. The scale is determined in Algorithm 2 in the supplementary material, Appendix A, available in the online supplemental material, as described in Section 5.2. Changing the camera position leads to a sparsification update, i.e., deciding what is shown or hidden in 3 steps. In the first step, as the camera serves as a pivot point for the shells, these are transformed to a new position with respect to it. In the second step, instances are associated through overlap with one of the shells. In the third step, multi-scale sparsification is performed. In this step, all instances are assigned a weight representing their priority of being hidden based on their abundance and distance from the camera. The visibility decision considers the multi-scale scene hierarchy and results in a sparsified model. These sparsification steps are described in detail in sections 5.1, 5.3, and 5.4. See also Figure 2. 5.1 Shell elements. The 3 shells define concentric bounding geometries around the camera and are responsible for preserving the viewer's comfort zone. Visible collisions of the camera with the innermost shell's instances should be avoided. In contrast, structures farther away from the camera should be perceivable, which requires sparsification in the middle and outermost shells at varying degrees. This method somewhat invokes the experience of using a vehicle lights at night. Nanotilus sparsification realizes gradual visibility management through 3 nested shells surrounding the camera to avoid the sudden disappearance of instances in front of the viewer. The outermost shell performs the initial stage of sparsification. The middle shell performs a further sparsification, and the innermost shell hides all instances obstructing the camera movement. Each shell has a different visibility percentage, i.e., the visibility percentage of the innermost shell is set to 0.0, which means all instances are entirely hidden to avoid collision with the camera. The visibility percentage increases with each larger shell. In the middle shell, only the scarcest and vital instances remain visible. In the outermost shell, more instances populate the shell space. Outside the outermost shell, visibility reaches 1.0, meaning that all instances remain fully visible and are shown. Altogether, the number of nested shells, the gradual visibility change between them, and the animated opacity transition between visible and hidden instances result in a smoothly perceived sparsification. In principle, the shells can take on any 3D geometric shape where a collision query can be solved. We tested several shell geometries, such as nested ellipsoids, nested cubes, and nested egg shapes. The latter geometries are loosely similar to a perspective viewing frustum, but with a limited sparsification zone. We concluded that nested ellipsoids provide the most immersive experience, especially when opening compartmental boundary structures. We used the standard ellipsoid equation, 59, to mathematically define the shell geometry of Nanotilus, where px, py, pz is a point on the surface, x, ey, ez is the center point of the ellipsoid, and a, b, and c are the scaling parameters for each coordinate axis. Px minus x, 2a2 plus, py minus ey, 2b2 plus, pz minus ez, 2c2 equals 1, 1. View source. The shell size specifies the volume of the sparsification region. Nanotilus updates the shell size based on the bounding sphere of the target instance when a new target is selected. Nanotilus interpolates between the current shell size and a newly estimated size based on the bounding sphere of the new target instance during the path traversal. To compute the final ellipsoid size from the target bounding sphere, we assigned its radius to the smallest parameter of the innermost ellipsoid and updated other ellipsoid parameters to preserve the original ratio. Accordingly, we update the parameters of other 2 outer ellipsoids to preserve the scale ratio between them. Another possibility is to select the innermost shell with an overproportion size, as it is the most important one that represents the comfort zone. The illustration in Figure 4 depicts the results of 2 different inner shell sizes. A larger inner shell produces a faster sparsification, leading to a sharper transition between sparsified and non-sparsified regions of the model. The middle and outermost shells in this comparison have the same size. Figure 4. Illustration of the sparsification process with different sizes of the innermost shell. The right image has a larger innermost shell. The right sides of both images display the resulting sparsification, whereas the left sides illustrate the shell membership in colors. The red color represents the instances that belong to most inner shell. The green and yellow colors represent outer shell's instances. A larger inner shell produces a sharper transition between sparsified and non-sparsified regions. Show all. 5.2 Scale determination. The proposed multi-scale sparsification scheme is unequal in terms of how the instances are sparsified. In the framework, the instances are hierarchically organized in a tree, similar to the commonly known scene graph structure. When a particular instance is close in the hierarchy to the target instance, e.g., example, being its parent or grandparent, sparsification is performed on a lower granularity level, i.e., leaf instance level. When the target instance is more distant from the instance, it will be sparsified with higher granularity. The children of a target instance are not sparsified as they constitute the target instance under inspection. To automate multi-scale sparsification, we define the following instance addressing scheme. Each instance is assigned a unique ID and a hierarchically composed ID address. We use the ID address of the target instance to determine the scale of sparsification for a particular instance. The similarity between the instance ID address to be sparsified and the target instance ID address determines the sparsification scale. We explain the concept with a simple example in Figure 5. A schematic multiscale model is depicted at the top left. Below is the corresponding hierarchical tree, where each level in the tree represents a distinct scale. The instance's depth is the number of edges from that instance up to the tree's root. The address definitions for each instance, too, based on the IDs of its own, its parents, and its ancestors are on the right. The sequence of IDs along the path from the root to an instance defines the ID address of that instance inside the 3D model. For example, the ID address of the green circle is 0.4.7. This address indicates us that to observe instance I7, we must sparsify instance I0 first, followed by instance I4. Based on the above address, there is no need to sparsify the blue triangle. If we decide to hide it, we must consider the entire subtree below the blue triangle to be a single element and hide it all at once. We can realize this if we compare the ID address of the target instance, i.e., 0.4.7, with the ID addresses of the blue, green, and yellow triangles, which are 0.1, 0.1.5, and 0.1.6, respectively. The scale-based ID of an instance is the first ID in its ID address that does not match the corresponding ID in the target ID address. Thus, for the blue, green, and yellow triangles, the scale-based ID is 1. Therefore, if sparsification is used, it hides level 1 instances, where the root is level 0. The final visibility decision concerning every instance relies on its scale-based ID. In the example, the visibility of instance I1 overrides the visibility values of the green and yellow triangles. Therefore, if we decide to remove the blue triangle, we also eliminate all of its children, i.e., the yellow and green triangles. Figure 5. Left top, illustration of a scene containing a multi-scale model. Left bottom, hierarchy of the multi-scale model. Each tree node is associated with a unique ID. Right, ID addresses of instances. Show all. The sparsification has to consider the previous target instance along the journey, too. For example, in Figure 5, let's assume the previous target instance is the green circle, and we select the green rectangle as the new target instance. Then, the scale-based ID of the yellow, green, and blue circle is 4. When we are inside the model closely observing target I7 and we switch to the new target instance, the whole I4 subtree disappears as a result of multi-scale sparsification. More natural behavior is to sparsify the previous target on a lower granularity level. Therefore, we calculate the scale-based ID of an instance by comparing it with the current and the previous target ID addresses. This procedure is called scale determination and is listed in Algorithm 2 in the supplementary material, Appendix A, available in the online supplemental material. Because the model is static, the ID addresses of model's instances are computed once after the model and hierarchy are loaded. Figure 6 shows an example of using the scale determination. Figure 6. Illustration of the scale determination result. In this example, the target is one of the plasma proteins, thus, sparsification is on the virus scale. The whole virion has the yellow membership, which means it belongs to the most outer shell because this virion partially intersects with that shell. Show all. 5.3 Membership identification. Nanotilus generates endoscopic views where the scene elements surround the viewer. It only sparsifies instances lying at least partially inside the shells. The mathematical description of the shell geometry is used to determine whether the bounding sphere of an instance intersects one of the shells. All shells are tested for intersection. If an intersection exists, the computation ends, and the instance is considered a member of the smallest shell it intersects. If the bounding sphere of the instance does not intersect with any shell, it has membership to the region outside the outermost shell. We compile additional information such as the number of visible and invisible instances in each shell and their distances from the camera, with the membership information during one compute shader call. Furthermore, we determine the number of visible instances per type, which is helpful for evaluating the importance of the types. 5.4 Sparsification Update. Sparsification is realized in two consecutive phases. The first phase does not consider the scale, where some instances that intersect the shells are selected for sparsification. The second phase considers the scale, where the sparsification decision from the previous step may be overridden by the sparsification value of one of the instance's ancestors in the model hierarchy. Phase 1. Initial sparsification. After membership identification, we know which instances are inside the shells. The shells are associated with the visibility percentage, determining the limit of how many instances inside the respective shell can remain visible. This initial sparsification selects instances that should be hidden and updates their visibility values accordingly. Every instance that is located outside the shells should not be sparsified. If the instance was hidden previously due to a prior intersection with the shells, it should now be visible again. Otherwise, a previously hidden instance remains hidden to maintain visual coherence as long as it is inside one of the shells. On the other hand, if the instance is visible and inside one of the shells, the algorithm checks every instance inside the shell for each shell to determine whether the desired number of invisible instances inside the shell has already been reached. For a shell element that has n instances and visibility percentage p, this threshold is computed as n-pn. If the number of invisible instances is still not achieved, each visible instance is a candidate. To be hidden. A weight is associated with each candidate instance that represents the instance priority to be hidden. Abundant instances and those located closer to the camera are assigned a higher priority of being hidden, while important instances are assigned a higher priority to remain visible. The weight is affected by two values: the distance from the instance to the camera and the importance of the type, computed as the complement of the ratio of instances of that type that remain visible inside the sparsification region. This is depicted in Figure 7, where the importance of the red molecule is calculated as 1-2/2 plus 10. The weight is calculated as follows. W equals importance 0, 1, dist 0, 1, 2, view source where importance represents the importance of the type, normalized to the range 0, 1. 0 corresponds to the lowest importance and 1 corresponds to the highest importance. Moreover, dist represents distance to camera, also normalized to the range 0, 1, where 0 is the closest and 1 is the farthest distance inside the sparsification region. A smaller instance weight W indicates a stronger candidate for being hidden. The algorithm sorts the candidate instances based on weight. Finally, the instances with the smallest weight are hidden until the threshold is achieved for a given shell. The pseudocode of initial sparsification can be found in Algorithm 3 in the supplementary material, Appendix A, available in the online supplemental material. Figure 7. Illustration of the sparsification process. The instances are sparsified based on the importance of the type, cyan or red, and membership to a shell. Low saturation colors represent hidden instances. All instances in the innermost shell have been removed regardless of their importance to avoid the block view. Some abundant instances have been removed from the second and third shells. Show all. The leaf instances are the basic building blocks of intermediate instances. Thus, selecting a leaf instance means its ancestors are also indirectly selected. Algorithm 3 applies only to the leaf instances, and once an instance is selected, the instance and some of its ancestors are hidden. The algorithm propagates the hidden status from the leaf instance through the ancestors until it reaches the ancestor that has an ID which matches the leaf instance's scale-based ID. Phase 2. Multi-scale sparsification. To convey the model's multiple scales to the user, multi-scale sparsification should be applied. In the previous step, specific instances have been selected to be sparsified. However, based on the scale-based ID, that sparsification may be overridden by the value of one of that instance's ancestors. The scale-based ID is given by the scale determination algorithm described in Section 5.2. In the multi-scale sparsification stage, the Nanotilus uses the scale-based ID to determine the final visibility of every leaf instance, depending on the hidden/unhidden status of the ancestor on the level of the current scale value. For every leaf instance, we fetch the sparsification status of the instance that has an ID corresponding to the scale-based ID and use it to update the sparsification status of that leaf instance. The multi-scale sparsification is formally described in Algorithm 3 in the supplementary material, Appendix A, available in the online supplemental material. Some instances in the model are so valuable that they should remain unhidden for the entire journey. For example, non-local genetic molecules, such as RNA, occupy a large space. However, their strand-like structure is sparse enough. Therefore, these non-local structures are never hidden. Instead, they are pushed away from the innermost shell. The displacement direction is computed based on the strand's control points positions and the shell's center position. The pushed control points return to their original positions after they leave the sparsification region. Instance fading effect. When instances become suddenly hidden or unhidden in the sparsification phase, it creates a visual popping artifact, which is inconvenient during the guided tour experience. Viewers must involuntarily redirect their gaze toward the visual popping position, which disturbs the experience. Therefore, instead of suddenly hiding or showing instances, we introduce the fading effect of the instances that change sparsification status. In other words, once the status of an instance changes from hidden to unhidden, or vice versa, as a result of the sparsification stage, the transparency of that instance is gradually increased/decreased with every rendering call until it becomes fully transparent/opaque. With that, the user perceives sparsification as a smooth process rather than a discrete event. The fading effect is achieved by the rendering of the scene in two independent passes. Only opaque instances are rendered in the first pass, whereas transparent instances with the corresponding alpha transparency are drawn in the second pass. The transparency change is animated over several frames. This change is performed as an off-screen rendering into two frame buffers objects, FBOs, which are composited using alpha blending. Section 6. Remaining elements of Nanotilus. In journey planning in Section 4, Nanotilus computes a path connecting target instances, which is primarily collision-free. The animation controller interpolates the path into a high-order curve and positions the camera along that curve based on the journey's progress. Every time the camera position is updated, sparsification is also updated. The shell elements are oriented so that their forward direction are aligned to the tangent on the curve, which results in the perception that the user is inside the Nautilus submarine. As our shell element is ellipsoid, the sparsification of the model is stronger in the forward direction and weaker orthogonal to it. Furthermore, the animation controller is responsible for triggering text-to-speech events. As the path connects node, pi, the sequence of instances S can be obtained as S equals P1.ref, Pn.ref. From journey planning, every type T is associated with a text snippet text, T. The animation controller synchronizes the camera with the text-to-speech synthesizer. Before the next step along the journey, it fetches the target instance C. Then, the camera traverses to target instance C, and the narration snippet text, T, is played in the form of audio. After both the camera traversal and narration are finished, the user can freely explore the current part of the model. Once the exploration is finished, the animation controller continues to target instance C+1. During the guided tour, the structural information annotating the model is augmented with audio narration and labels. Labeling provides the user with additional descriptive information about the model. Moreover, labels help the user associate the information from the narration to the particular instances. We integrated the labeling approach by Kouřil et al. 1860, which identifies the types of instances currently visible and places labels for the representative instances for all types in the current viewpoint. However, restricting the labeling process to only once the camera rotation and movement is completely stopped is infeasible for the VR environment. If the user observes the model through a VR head-mounted display, HMD, the camera orientation and position are tracked and continuously updated by the HMD. The camera never stops, there is slight movement at all times. Therefore, we extended the original method to label the model several times, transiting from one instance to another. In other words, if the camera navigates from structure C to structure C+1, the arc length of the path is calculated. As the camera progresses along the path, after it reaches 25%, 50%, 75%, and 95% of its arc length, labeling is performed based on the current view direction. This labeling provides the viewers an actual description of the model even if they rotate their heads 180 ring operator along the journey. Section 7. Technical implementation. We implemented Nanotilus using the Marian framework, 61, employing an imposter rendering pipeline based on the work by Music et al. 62. The entire framework is implemented in C++, OpenGL, and GLSL and relies on the Qt library. Nanotilus is implemented using GLSL compute shaders with only small data transfer between the CPU and GPU. As the target environment for the presentation of the resulting guided tours, we used the HTC Vive Cosmos. Therefore, we implemented OpenVR support in the framework. The target model typically consists of several thousands of instances, all formed by millions of atoms, with a hierarchy that defines the logical structure of the model. The illustrations of both hierarchies of the HIV and SARS-CoV-2 models are presented in figures 11 and 12 in the supplementary material, Appendix C, available in the online supplemental material. The HIV model was generated by Scripps Research, 163. The SARS-CoV-2 model was created using our recently introduced modeling approach, 4. The virion model was enclosed in the model of blood plasma to create conditions similar to the HIV model. We automatically generated guided tours for these two molecular models, HIV and SARS-CoV-2, in blood plasma, with comparable numbers of molecules. 18,515 for HIV and 14,583 for SARS-CoV-2, and lipids, approximate 200,000 in HIV, 140,000 in SARS-CoV-2. Both models have RNA strands. We authored a script for each model, 340 words with 11 mention types for HIV and 354 words with 10 mention types for SARS-CoV-2. The sample screenshots from the HIV tour are presented in Figure 8 and Figure 1. Figure 8. Illustrative stereo pair images from the HIV guided tour. Left, Nanotilus penetrating the membrane of the virion. Right, Nanotilus focused on an instance inside the virion. Show all. After the performance optimizations described in the supplementary material, Appendix B, available in the online supplemental material, we set the resolution to 1064 by 1256 pixels per eye. The application ran on an Intel Xeon Gold 6242, GeForce 3090, Windows 10 Education, Qt 5.14.2 with 25 FPS per eye, on average. While the FPS recommendations for VR are typically higher, the frame rate was sufficient for conducting the user study to assess whether Nanotilus preserves an immersive experience. Section 8. User study. We invited 29 bioscience students to participate in a VR user study. In the study, participants conducted 2 guided tours through 3D models of viruses, HIV and SARS-CoV-2, using a VR HMD. The study took around 20 to 30 minutes, and participants were compensated with gift vouchers, $50 each. The Institutional Biosafety and Bioethics Committee at KAUST approved the study. The focus is on the formal comparison of the outside-in and inside-out views, Nanotilus, to explore the main contributions of the approach in a user study. We chose Molecumentary 5, which uses a cutting plane as an occlusion management technique to guide the user through an automated story as a state-of-the-art baseline condition representing the outside-in view. Thus, the two conditions primarily differ from each other in how they visually present the current focus of the story to the user. In contrast to Molecumentary, Nanotilus allows users to become fully immersed in the instances and feel as if they were inside the model. Increasing the sense of presence is also likely to increase learning and understanding. 64. Therefore, we hypothesize that users would report a deeper understanding of the 3D structure of the presented molecules despite the density of the model due to our smart visibility handling using the inside-out view. 8.1 Stimuli and Apparatus. The textual story was split into separate textual snippets for each target instance. These snippets were presented using text-to-speech synthesis. As the focus of the study was on visual scene perception and not navigation, we used the Wizard of Oz method to guide the users through both scenes. Upon verbal request, the experimenter advanced the story so that the user was transitioned to the next target instance, and the next section in the synthesized audio narration was played. At each target instance, the tour was paused, and the users could look around freely to inspect their surroundings. The users stood while viewing both scenes using an HTC Vive Cosmos. As we employed the Wizard of Oz method with speech commands, users did not receive any pointing or teleportation controllers. This way, inexperienced VR users also could navigate the scene efficiently without introducing a potential confounding effect. 8.2 Study Design and Procedure. We employed a within-subject design with one experimental factor, interface, Nanotilus or Molecumentary. Figure 13 depicts the SARS-CoV-2 scene for both study conditions. To compensate for learning effects, we counterbalance the order of appearance of the two interfaces and the assignment of the two data sets to the two interfaces. To measure the user's sense of presence and overall impression, we collected the following dependent measures. First, after each condition, users completed a questionnaire related to the sense of presence. We adopted a widely adopted presence questionnaire, 64, by selecting only questionnaire items referring to the visual input and overall user experience. Second, we issued a final preference questionnaire in which users rated their overall impressions of the two conditions and provided free written feedback on each condition after exposure to both conditions. The complete questionnaires, responses, and procedures are presented in the user study document in the supplementary material available in the online supplemental material. Of the 29 students, 17 were female and 12 male, ages 22 to 39, with a mean age of 27.1. All students were master's degree or PhD students of bioscience. Their self-reported knowledge of SARS-CoV-2 and HIV was an average of 4.5 and 3.8, respectively, on a 7-point Likert scale. With the bioscience student sample, we assumed that all users were generally interested in the topic, yet not experts with deep prior knowledge of the viral structures. 8.3 Study Results. Presence was measured using the results from the Sense of Presence questionnaire. For the 15 items in the Adapted Presence questionnaire, 3 responses presented in Figure 9 yielded significant results. In all 3 cases, the responses were significantly higher for Nanotilus than Molecumentary, Figure 9. Participants were more involved, visually and overall, in the Nanotilus condition and could more easily inspect the structures from multiple viewpoints. The remaining questionnaire results are provided in the user study document in the supplementary material, available in the online supplemental material. Figure 9. Items from the Sense of Presence questionnaire displaying significant results of the Wilcoxon-signed rank tests. Show all. The overall average preference rating on the 7-point Likert scale was slightly higher for Nanotilus, 4.25, than for molecumentary, 4.07, but this difference is not statistically significant. Z equals minus 0.787, P equals 0.431. We performed open coding to qualitatively analyze the user's subjective textual feedback of both conditions to understand the perceived strengths and weaknesses better. 2 independent coders established 4 feedback categories: experience, engagement, and overall user experience, spatial cognition, understanding of scales and spatial relations, locomotion, feedback concerning movement and scene interaction, and guidance, orientation, and ability to follow the story. All coded utterances were categorized into positive and negative feedback, Figure 10. The feedback confirms that Nanotilus leads to a more positive user experience overall. For example, people commented that they liked how close I was to the structures, felt they were inside the virus, and found it very immersive. In contrast, molecumentary seems to provide an easier way to follow the story. Users commented that this outside-in view gives you an overview, is very clear, and uses good highlighting, whereas participants commented that they sometimes did not know where to focus using Nanotilus. Users criticized the lack of guide arrows or other types of annotation for the current objects of interest. Figure 10. User feedback for Nanotilus, left, and molecumentary, right, coded into 4 categories. Bars indicate the amount of positive and negative feedback for each category and condition. Show all. For both interfaces, some users expressed the wish to have more control over their location inside the scene. For example, one user stated, "Wished I could walk closer inside or walk backward away from the structures using Nanotilus." 2 users mentioned that they would like to observe selected structures from different angles, 2 for Nanotilus, 1 for molecumentary. Using molecumentary, users wished to go inside the virus and see what is there and see the structures more closely. Even though steering locomotion is known to induce cybersickness symptoms 65, only 2 users reported slight feelings of dizziness, both for Nanotilus. 3 users explicitly mentioned that they did not feel sick or dizzy, 1 for Nanotilus and 2 for molecumentary. One strength of Nanotilus inside-out view for molecular visualization is its ability to enhance spatial cognition. According to the users, it intuitively showed the size of the molecules and their relation to one another so that it is nice to see how small some of the constructs are compared to others. Also, cells are quite densely packed. In contrast, one user commented that the scale using the molecumentary tour was harder to comprehend as the virus took up most of the visual field in front of the view, making it seem larger in comparison to the virus in the Nanotilus tour. The comprehensive coded list of user comments is presented in the user study document in the supplementary material, available in the online supplemental material. Section 9. Discussion. The Sense of Presence questionnaire results and user feedback indicate that Nanotilus immersive inside-out view increases engagement and involvement. However, this increased engagement does not automatically lead to a higher acceptance of Nanotilus as compared to a state-of-the-art outside-in view using a clipping plane to resolve occlusions. In the latter case, users reported a clearer overview and could therefore more easily follow the narration. Studies comparing looking into abstract data, such as scatter plots and graphs, as opposed to looking onto the data, have reported similar results. Users are more engaged inside a dataset, 54, and tend to feel more present, 55. Moreover, they can gain new, insightful perspectives on the data, 56. However, they also experience a higher task load, 54, more loss of overview, 55, and an increased tendency towards cyber sickness. 56. In summary, immersing into the structures seems to trade the ability to maintain an overview against a more pronounced sense of presence, i.e., a sense of being in the environment. 64. Results from the subjective user feedback indicate that this increased sense of presence can improve users' spatial understanding of the visualized structures. It is known from VR research that immersion can improve spatial understanding. 66. Yet there has been no scientific evidence so far whether an inside-out view can improve the spatial understanding of a molecular scene compared with an outside-in view. Future work must consider ways to fluidly transition between a clear outside-in overview of the narration to an inside-out view for a detailed and more engaging inspection of structures to combine the advantages. Section 10. Conclusion and future work. We developed a novel guided tour generator that can transform a 3D model and associated script into an immersive guided tour about the biological nanoworld. On top of multiple existing technologies, we developed a new journey planning technique and a new sparsification method, which enable an engaging, immersive experience when coupled together. There are 2 steps to improve the current software prototype: performance acceleration and a new sparsification technique that strengthens the sense of orientation while preserving the immersion. The Nanotilus guided tour generator is designed for a linear narrative. However, in principle, it is easily expandable to support non-linear storytelling. In such a scenario, the story has several paths. It branches and forms a story tree or even a story graph. With such a representation, the interaction can be as follows. The user visits a particular node and is offered several ways to proceed, or the user engages in conversation with the system. And the most related edge in this story structure would be followed. Conversational visualization is an important topic to further investigate in this particular setting or visualization in general. On the author side, this means not only one story needs to be authored, but the entire guided structure is authored with various degrees of automation. In this paper, we focused on assisted forms of interaction, as it is frequently the choice in explanatory visualization scenarios. Based on the user study, we consider the proposed sparsification strategy feasible and conceive a combination of sparsification geometry for molecumentary and Nanotilus. In principle, we can smoothly combine these 2 sparsification geometries, provided both are formulated as implicit objects. With such a combination, we can occasionally enable a general oversight view using molecumentary sparsification, which is blended back into the immersive experience of Nanotilus. Thus, we do not require proxy elements, such as a miniaturized world overview, which requires divided attention from the users. The degree of sparsification was the control factor in our study. However, the navigation through the void spaces could also have a strong influence on the perception. There are indications in prior work that support this consideration. For example, in VR training simulations, the amount of visual details had an influence on the training success. 67, 68. In VR crowd simulations, the density influences where participants look. 69. We can therefore expect that the number of visible instances, how they are presented, and how the user can navigate through them also have a considerable influence on the user's experiences. We consider this as an important point for future research. In the Nanotilus guided tour generator, we provide the itinerary from the author's script. Although this itinerary results in an engaging visual experience, the viewers passively consume the provided information. Another method could be to provide the viewers with the option to create their own stories throughout the model, potentially leading to even stronger engagement. Nanotilus currently follows a predefined tour plan. In an interactive scenario, multiple options exist regarding where to go and what to explore. Another challenge is to create an explorative environment, which still guarantees a specific learning outcome. For this purpose, subtle gaze direction and flicker guiding techniques, 70, can unperceivably guide the viewers to explore specific structures with the illusion of free will, where viewers would feel they discovered the intended target instances by choice. Acknowledgements. The authors would like to thank Nanographics AT for providing the Marion software, Alex Kayumjian for insightful comments, and Jules Verne for inspiration. Ruwayda Alharbi and Ondřej Strnad are co-first authors. This work involved human subjects or animals in its research. Approval of all ethical and experimental procedures and protocols was granted by Institutional Biosafety and Bioethics Committee, IB.